Symmetry to start with today, and we're going to have three types of symmetry that we're looking at. And you may have touched on symmetry in Algebra 2. I know we didn't do a ton of algebraic testing in regular Algebra 2, but you may have in honors. Mostly what we were looking at was when they had line symmetry where it would fold, or point symmetry when it would rotate. These are a little bit more specific. So we're looking at our even, which is Y symmetry, Y-axis symmetry, so it's very specific. If we were looking at a graph, say, I'm just going to give us a little bitty sketch here. Something like a parabola that's on our Y-axis. This is even because it is exactly the same when reflected across the Y-axis. So the way we're going to test for that is we're going to substitute in for the x, negative x, the opposite of x. Because the opposite of x should be exactly the same as what our x was. It matches across our y-axis. It is also called even. You don't have to use that name, but I was just tossing it out there because you may have heard it before. X-axis symmetry doesn't have a special name. It's just called x-axis symmetry. And that would be something that is exactly the same across the x-axis. So that sideways parabola we drew yesterday has x-axis symmetry because it's exactly the same on either side of our x-axis. You replace y with minus y and simplify to see if it has symmetry. Origin symmetry is when it's symmetric about our origin. It's usually called odd. Things like our cubic has origin symmetry, because what that is a rotational symmetry. If I put a pin in it right at the origin and spun it, it would match back up. But we're going to test all these algebraically using what we have here. So to test for y-axis symmetry, we replace x with negative x. To check for x-axis symmetry, we replace y with negative y. And to check for origin symmetry, we replace both. X with negative x, y with negative y. So we're going to practice this with 4 equations, and we're going to do all 3 tests for all 4 equations. They're not super long. But just so that we see when we write these out, don't put them super duper close to each other. Because we're going to do 3 replacements. And I know I still got a couple of us writing, so I'm going to give you guys a couple more. A minute or 2. This is from actual Nintendo Land. All right. Most of the pencils have stopped. I'm going to change it in 5, 4, 3, 2, 1. Okay, so we're going to be given a problem like this, and it says determine the type of symmetry. So we are going to do our little tests. So we're going to test for x-axis symmetry, y-axis symmetry, and origin symmetry. And yes, you have to do all 3 tests even if you find one. These are going to fall off my head if I look downwards. So our first test we're going to do is I'm going to test for y-axis symmetry. And what we do for our y-axis symmetry is I'm going to replace the x with the opposite of x. So replacing this guy. So we're going to have the opposite of x equals negative y squared. And then we're going to try and simplify it back to be what it was at the top. In this case, it's an x equals. So what would we do to get this back to be an x equals? Multiply by negative 1. So that will give me x equals y squared. Is this exactly the same as our original equation? No. So this does not have y symmetry. Okay. To do our x-axis symmetry, That's when we replace the y with the opposite of y. So we're going to have our x equals the opposite of negative y squared. What's going to happen here? Yeah, because negative y, quantity squared, is the exact same thing as y squared, right? So this, when I simplify, becomes x equals negative y squared. It's the exact same thing. So does this have x-axis symmetry? Is this exactly the same as this was? What's up? When I have a power, I can't multiply these together. This has a power. But negative y squared is the exact same thing as y squared. Just like negative 2 squared would still be 2 squared. It's the same exact thing. So is this equation the exact same as this one was? Yes. So this does have x-axis symmetry. So this has x-axis symmetry. We're still going to do our origin test. So we're going to check for origin symmetry. And to do that, we're going to do both of those. So we have our minus x equals the opposite of negative y squared. We're going to wind up doing kind of both simplifications that we did above. So first thing I'm going to simplify is my y. Minus y squared is the exact same thing as as y squared. So minus x equals the opposite of y squared. And then just like we did for our y symmetry, if I divide by negative 1, we get x equals y squared. So is this the exact same as our original equation? Nope. So this does not have origin symmetry. So this only has x-axis symmetry. That's what we're doing on this one. That's all we're trying to do on it, is just add the symmetry. What's up? Mm-hmm. Yep. And we're going to practice this a couple more times because it is awkward. It feels weird. Yes, dear. Yes. If you're asked to find the type of symmetry, you have to test all three. Because there are some functions that have more than one kind of symmetry. And we'll see that eventually. Today. All right, so let's look at this next one. Y equals 1/4 x cubed. Oh my gosh, this headband is going to slide every time I look down. So we're going to do our y symmetry test first. That's when I replace my x with the opposite of x. We're going to have y equals 1/4 times the opposite of x cubed. Oh. Sorry, this was our y symmetry test. Y symmetry. We replace the x with the opposite of x to determine if it's y symmetry. So when I cube a negative number, does that always have to be positive? No. So it could be negative. So this we could simplify as the opposite of 1/4 x cubed. Because negative x when cubed would be negative. So we can do that. What's up? I can. Because when I have negative x times negative x times negative x, I'm going to bring that over here. Minus x, minus x, that's minus x. Well, these two would be positive, x squared times minus x. That's the same thing as minus x cubed. Okay, so you can do it this way and think about it this way. So does this have y symmetry? No. Let's try our x symmetry. That's when I replace my y with our negative y. So we're going to have the opposite of y equals 1/4 times x cubed. I want to get it back to a y equals and have everything fully simplified. So what would we do? How do I get it back to a y equals? Divide by -1. So we have our negative 1/4 x cubed. If you said it, say it louder. Because all I heard was... Remember, I'm old. So does this exactly match our original equation? Nah. So this does not have x symmetry either. So now we're going to do our origin test. That's when we do both. So we're going to have our opposite of y equals 1/4 times the opposite of x cubed. And we're going to wind up doing a lot of the same simplifications we did. So just like with our y symmetry, that opposite of x cubed makes this side negative 1/4 x cubed. And then what do I do to get my y by itself? Divide by -1. So we have our y equals 1/4 x cubed. Does that exactly match what we started with? Yes, it does. So since this matches this exactly, that means we have origin symmetry. So we have origin symmetry on this one. Okay, so it's a little awkward and kind of long, but we can do this. We're going to do 2 more. So we're going to determine the type of symmetry. So I've got y equals negative 3x squared plus 4. So we're going to start with doing our y symmetry. That's when we replace our x with the opposite of x. So y equals negative 3 times the opposite of x squared plus 4. When I square a negative number, it's still going to be positive. So minus x when squared is exactly the same thing as x squared. So does this have y symmetry? Yes. Since this is exactly the same as this, we have y symmetry. I'm going to change the color real quick. Since this is the same as this, we have our y symmetry. There we go. We still need to do our other tests, though. So then we're going to check for x symmetry. And we're going to replace our y with the opposite of y. So the opposite of y equals negative 3x squared plus 4. And we want to get this back to a y equals, so what do? Divide by -1. So we have our y equals 3x squared minus 4. Is that exactly the same as our starting function? No. So do we have x symmetry? No. Let's test for our origin symmetry. We're going to do both. So we're going to have our minus y equals negative 3 times our negative x squared plus 4. So just like on our y symmetry test, that negative x squared is just the same thing as x squared. So I can cancel that negative out. And then how do I get my y by itself? Divide by -1. And we get the exact same thing we did for our x symmetry test. So do we have origin symmetry? Do we have origin symmetry? Nah. Most frequently, your functions will have just one kind of symmetry or no symmetry. But it is possible for it to have more than one. So that's why we always test all three. So let's do one more of these symmetry tests and then we'll move away from that because they get repetitive. So we've got this x squared plus y squared equals 4. So let's do our y symmetry test. So for y symmetry, that's when we replace our x with our opposite of x. Oh, good. We have email back. So what's going to happen when I square the opposite of x? Positive. So this is the same thing as x squared plus y squared equals 4. So does it have y symmetry? Yes. Because this piece exactly matches this piece. Let's check for ooh, wrong pen. Let's check for x symmetry. That's when we're going to take our x squared plus the opposite of y squared equals 4. What happens when I square the opposite of y? Becomes a positive. So I have x squared plus y squared equals 4. So do we have x symmetry? Yes. Ooh, fancy schmancy. Because this matches that same set of equations. So we also have x symmetry. One more test. Let's check for origin. Surely it's not going to have all three. We have our opposite of x squared plus the opposite of y squared equals 4. That is a y. Looks kind of xy, but that's a y. So what happens when we square the opposite of x? Same thing as x squared. What happens when we square the opposite of y? Positive y squared. So do we have origin symmetry too? Yes. What the heck is happening here? What shape is this? What is this? What would this look like if we graphed it? You remember? If I have x squared plus y squared equals a number. It's not slope. Geometry. Think geometry. Closer. This is a circle. It's a circle. X squared plus y squared equals a radius. And that is a circle right on the origin. Because we usually did, x plus h squared, y plus k squared equals that radius squared. So that's a circle right on the origin. That's why it has all the symmetries. We just drew a circle around our center. Okay, so questions about our symmetry tests? Nah. Okay. So the next thing we're going to talk about are intercepts, finding x-intercepts and y-intercepts. We definitely did this in Algebra 2, but we may not have done it since then. We use this a lot when graphing, especially lines. Our x-intercepts, also known as our, roots or solutions or zeros. We use that a lot, especially in like quadratics and polynomials. When we're talking on graphs and on functions, that's when we have a point x comma 0. It's on our x-axis. It's where whatever our shape is, wherever our graph is, crosses our x-axis. So what we know about an x-intercept is that my y must be 0. It's where we cross the x-axis. Where graph crosses the x-axis. And we find it by setting y equal to 0. We know for an x-intercept, my y has to be 0. So we're going to find x-intercepts by making y be 0. We'll substitute in y equals 0 and solve it. Solve for x. It's very, very similar for our y-intercept. It doesn't get more names, though. Our y-intercept's just our y-intercept. But it happens at the point 0, comma, y, because it's when the graph crosses the y-axis. So what we know about our y-intercept is that our x equals 0. So we're going to find by setting x equal to 0 and solving to solve for y. So to find x-intercepts, we substitute in y equals 0. To find y-intercepts, we set x equal to 0. And shock of all shocks, I wonder what we're going to do next. But practice that. Oh, snap. So we're going to look at a few of these and find some x and y intercepts. So I'm going to start with our y-intercept here. So to find our y-intercept, that's when we know for sure x has to equal 0. So y equals, and I'm going to substitute in 0 for my x. 0 squared plus 8 times 0 plus 7. Substituting in 0 for every single one of the x's. So what do we get when we simplify this? What is our y-intercept going to be? 7, because 0 squared is 0. 8 times 0 is 0. So my y equals 7. So my y-intercept is at the point 0, comma 7. My x is 0, my y is 7. To find my x-intercepts, that's when I know my y equals 0. So we're going to substitute in 0 for y. X squared plus 8x plus 7. And what can I do to figure out what x is? Factor. What do we get when we factor? So we have our x, bless you, plus 7, x plus 1. Our pair of numbers that multiplies to make 7 and adds to make 8. So what are my solutions? X equals negative 7, x equals negative 1. So this one has two x-intercepts at the points negative 7, 0, and negative 1. 0. Questions on those? So we've worked with x-intercepts a lot. We haven't done as much with y-intercepts, but it's not super duper complicated. So we're going to do the same thing on this square root function. We're going to have our y-intercept when we set x equal to 0, and we're going to have our x-intercept when y equals to 0. So to find my y-intercept, we're going to set our x equal to 0. So y equals -2 square root 0 plus 9 minus 10 simplify it. Our 0 plus 9, it gives us just 9. What is the square root of 9? 3. When we're thinking about graphs, for the most part, we don't have to worry about plus or minus 3 because with square roots, we're only looking at that side. So one of them will wind up being extraneous if you do your plus or minus. You can always do that if you feel like it. If you do your plus or minus, you're just looking at this shape and figuring out which one is eliminated out, which will almost always be the negative one. So we can just focus on the fact that square roots look like this. We can just take our positive 3. So what is our y-intercept here? -16. -2 times 3 gives me -6 minus 10, -16. So our y-intercept is going to happen at the point 0, -16. Let's do our x-intercepts. That's we're going to set 0 for y. -2 square root of x plus 9 minus 10. What are we going to do first? Add 10. Then what? Divide by -2. So I have -5 equals our square root of x plus 9. Then what? Square it. So I have 25 equals x plus 9.
No.
Subtract 9. So what do we get for x? 16. So my x-intercept is happening at 16, 0. One more like this. So let's find our y-intercept for this one. Y equals, and we substitute in 0 for every single x. 0 plus 5, 0 minus 2. So what's our y going to equal? -5/2. 0 plus 5 gives me 5. 0 minus 2 gives me -2. If you write it like that, totally fine with me. Better grammar would be -5/2 or putting the minus with the 5. Either way is fine. Not I'm not mad at it. It's not wrong. This is better, but just barely. So our y-intercept is happening at the point 0, comma, -5/2. Closing. Now let's see if we can find our x-intercepts. So we're going to substitute in 0 for y. X plus 5 over x minus 2. We've worked with these before. What can we do? What's up? You can. Hard mode. Yeah, multiply both sides. I have an equal side. As long as I do the same thing to both sides, I can do whatever the heck I want. X minus 2. X minus 2. You could rationalize, but you're going hard mode that way. Because this is just going to still be 0. X plus 5. So what is our x going to be? X equals -5. So my x-intercept is going to happen at -5, comma, 0. When we have these rational functions, all I care is when my numerator is 0, because 0 over anything is a 0. Okay? So we've worked with x and y intercepts before, but it's been a minute. Questions on x, y intercepts? Questions on the symmetry? We got a little bit more. You're not done. Because I kind of teased it on the last one, where we were talking about that x squared plus y squared equals 4. Because the next thing we're going to play with is circles. Playing with circles. So this is the formula for a circle. And it marks the center at h comma k. And our radius is r squared. Filter out. Because for the rest of the day, we're going to play with circles and we're going to graph and feel them. So while you guys are writing this down, I'm going to pass out some graphs. You can also kind of like freehand these in your notes. It's not going to be super complex, but a lot of us like properly graph things because of what you have to manage. Alright, so x minus h, quantity squared, y minus k, quantity squared, gives us our radius squared. Make sure we pay attention to those pieces. Our signs inside our parentheses are always going to be opposite for our center. And this is always the radius squared. Super important. So what we're going to do is I'm going to give you an equation. We're going to find our center, we're going to find our radius, and we're going to give it a little sketchy sketch. They're not going to be perfect. My circles always look very squarish because I'm bad at drawing a freehand circle, and that's okay. So it's not super hard on the calculations here, but if I give you an equation like this, x minus 3 quantity squared plus y minus 1 quantity squared equals 16. So I'll put our little formula right above it so we can play a little match them up. X minus h quantity squared plus y minus k quantity squared equals r squared. So my first question is, what is our h? 3. What is our K? 1. What is our R? 4. So we have a center at the point 3, 1. So we start there. So at 3, 1. Oh, sorry, your radius is going to be half off your graph. And then I need a radius of 4. So when I'm drawing a circle, that means it goes out 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4 in all directions. I recommend sticking with, north, south, east, west, because we can actually see where it hits 4. Then just connect up those corners, giving it as much of a curve as we can. See what I mean? My circles all wind up kind of squarish. I am not an art critic. We do not need to get out compasses. We're getting it close enough. Give me your center. Give me our radiuses. Give me as much as we can. Okay? Let's do another one. X squared plus y plus 3 squared equals 9. So we need to find our H, our K, and our R. What is our H? 0. What's our K? -3. What's our R? 3. R squared is what our equation equals. So our center is going to be at the point 0, -3. So 0, -3. Hey, this one will fit on your graphs. Huzzah. And we're going to go out a radius of 3. So I'm going to go out 3, 1, 2, 3. This way? What's up? Yep. Definitely making sure we're paying attention. Totally. 0, -3. Thank you. Call me out. Sometimes I get excited and jump ahead. So I'm like, I want to draw a circle. All right. So my set, it's actually, 0, -3. It's my y-intercept, not my x-intercept. I just got excited. So now we're going to do our radius of 3. So I'm going to go out 3 to the right. I'm going to go up 3. I'm going to go left 3. And I'm going to go down 3. You do not have to draw the little line segments. I'm just trying to get you guys to like see where I'm going. If you just want to put dots, that works totally fine because this thing looks kind of like a wheel when I do that. So if you just want to do dots, you can, but I feel like that's really hard to see on the screen when I do that. So then we're going to connect them up, make it as circly as we can. Oof, there we go. I'm so good at drawing circles. Looks kind of like a peach, but whatever. We get the vibe. Okay. So we find our center, we find our radius, we give it a sketch. And we will stop there because we have 2 minutes. And I don't want us to take all the way up. So when you start looking at the homework and we're looking at the circles, they're going to give us equations like this, but they're also going to give us ones that don't look like this, and we'll talk about those tomorrow. All right, 3.2 is going to be due on Monday. We will finish up circles and talk about something else tomorrow. We have another piece of it. This 3.2 covers a lot.